for the values for the value of x1, y1 for the values of f of x1, y1 at these 2 points. So now I have 2 over xy and x squared plus y squared, both of them equal 0 and 4. I need to find the corresponding values of x and y. So solving these 2 equations will develop 2x and y equal to 0 and x squared plus y squared equal to 4. Unfortunately, I will have to pick the numbers. I will start with the first equation because it's a nonlinear system. So I will start to say I have x and y equal to 0. So either x equal to 0 or y equal to 0. So actually, going through the discussion of this part will leave you with it is either x equal to 0 or y equal to 0. Okay, if x equal to 0, I will use this data and go for the second equation, which means that y squared equal 4. And now I will have 2 points, 0, 2, or 0 and negative 2. And if we consider that y is the one who's equal to 0, and we start to put these values in here, I will have 2 and 0, or negative 2 and 0. So one of these points can give, actually these points will develop 0 and 4. So I will need just to pick one of them. I will consider 2 and 0. It's really very simple, simpler than the other values. I will choose 2 and 0. So let's give it a try. Okay, all of this is stated here. So this is the g. I will put 0 equal to 4. I'm searching for the values of x and y. This is explained here that I will put either x equal to 0, y equal to 0. I will make substitution in the second equation, which will develop that the y values is going to be positive or negative and so on. So I will choose to use 2 and 0. Now I will get the Jacobian of this matrix. The Jacobian is really very simple. I will start differentiating. So this is the Jacobian of J, which is very simple. Differentiating with respect to x give you 2y. Differentiating with respect to y will develop 2 of an x. The second function, differentiating with respect to x is going to be 2x. Differentiating with respect to y, so it's going to be a 2 over y. So the value of the determinant of j is going to be 4 y squared minus 4 x squared. This is the Jacobian. So using this value, and this is the Jacobian, as I told you. Okay, here we go. That's the Jacobian. Evaluating its value at 2 and 0, getting the results at 2 and 0, it's going to leave you with 4 times the value of y, so it's going to be 0, negative 4 times 2 to the power of 2, so you will have negative 16. Now I have that it is negative 16. Of course, at 2 and 0, the Jacobian of the main function, the value of the main function at 2 and 0, this is the Jacobian of g at 2 and 0, will be the values like this is going to be a 4, a 0, okay, 0, because you have y values, and the 4, this is going to be a 4 and 0, so this is the Jacobian. So getting the inverse j minus 1 at the point which is 0 and 4, it is equal to 1 divided by the Jacobian of g at the point 2 and 0, which means I will have to get the inverse of this guy. The inverse of this guy will be like this. So this is 1 over the Jacobian, which means the inverse is once more. This is the Jacobian of g, the determinant of the Jacobian at 2 and 0. So the next step, I will try to get its inverse, as I told you, which is very, very simple. for a 2 by 2 determinant matrix, if I want to get the inverse, in order to get the value of this guy, all I have to do is to replace the elements of the principal diagonal, giving the negative sign. So now I will get the inverse, which is this result. This is the inverse of this guy, which is going to be 0 and 0, -4 and the -4. And all of these values are going to be divided by the value of this determinant, which is negative of a 16. Here we go. And so the results will be 0, 1/4, 1/4, and 0, as you can see. And this is why this is going to be the correct answer, 0.25, and 0. Now you can see that we have used the advantage of this theory of the inversion. These problems are important. I want you to go through them, understand the procedure, how we need the Jacobians from the previous parts in our course, and how to make them all work together. This is really very important. By this part, I think this is all for the inverse function theory in Rn. What I need you to do is to try to go through the sheet and the workbook, because we may not have enough time. Any questions? Okay, perfect. I will continue with just a small introduction about the implicit function. Hopefully within this week, or at the most next Sunday, I will make a revision for the exam. So I will go with the first part in the implicit functions. The implicit function theory, it's one of the important theories generally in calculus. It's very useful in our study in SPE because it has a lot of applications in economical models. This is why it is important. And it's really very simple. The idea of the implicit function is that it's the theory behind it is a fundamental result in calculus that tells us when a relation of the form f and you have x and y equal to 0. If I can get y as a function in x, so instead of dealing with a total function equal to 0, it's going to be a function in x and in a function in x. This is the implicit function. Bottom line, try to get, if you can succeed in getting y as a function in x. So for this guy, which is certain type of function contains x and y, and it's going to equal to 0. If I succeeded in getting y as a function in x, so the function mainly will be x and f of x. However, f is continuously differentiable function of several variables, can be solved for y as a function of x near a point where certain conditions are met in simple terms. It guarantees that f of x, y equals 0 and the partial derivatives. This is the condition actually. In order to be able to get an implicit function, or to get y as a function of x, and you make this simple substitution, the derivative of f with respect to y shouldn't equal to 0. That's what's stated here. So for f, x, y equals 0, and the partial derivative with respect to y is non-zero, or in higher dimension, reinvertible, then there exists a function y g of x. So I can succeed in getting f of x and x as parts of the general function controlling these two variables, but just we have to be sure that the partial derivative of an f with respect to x is not equal to 0. Divided in the neighborhood, this is the function that we are searching for. The theorem is essential because it lets us express one variable, as I told you exactly, implicitly in terms of other variables. Okay, let's see these some introductory examples. If I have an elliptic paraboloid, this shape, it's called an elliptic paraboloid. Okay, the elliptic paraboloid in 3D, so if this is x and that's y and this is z, it's gonna be something as you have a second degree parabola and they make it to revolve about the z axis, so it's gonna deform this shape. One of the other examples, if I have something like, okay, it's like this. Let me try to graph it for you. So if I am in 3D, this is going to be the positive direction of x, this is the positive direction of y, this is the positive direction of z. So actually, we are talking about a parabola in this shape, and it's going to be revolved about dz. So this is the shape that we are talking about, as you can see. If I sliced this shape, if I try to slice it just at z equal to 1, I will make a cut. At z equal to 2 or k, I will make another cut. And then I will project them into by 1, the xy plane. What's going to happen? So this is actually at certain point, and I will cut and project this cycle into by 1, the xy plane. And once you try to do so, it means that this is the main equation of the paraboloid. So at z equal 1, it means that we are getting the shape at z equal to 1. The value is going to be x squared plus y squared equal to 1. If I make this projection into the by 1, this is going to be the shape. So at z equal to 1, if I cut, I will get the unit circle. At 2, if I cut, I will get a second circle, and so on. So it's going to be, if I'm dropping this into by 1 and getting the projection, it's going to be cycles, circles, as you can see. Let's consider the first or the simplest circle of them, which is the circle at z equal to 1. So simply, it's going to be the unit circle, which have 1 and 0, negative 1 and 0, 0 and positive 1, 0 and the negative 1, and the equation will be x squared plus y squared equal to 1. So mainly, this is from r squared into r. I'm taking stuff from x and y and project it into r. This is going to be the projection of the plane z equal to 1, so x squared y squared equal to 1. And now we have h of x equal to 1. Can I get, for this function, which is x squared plus y squared equal 1, the y as a function in x? We will see. Yes, simply, we can take x squared plus y squared equal to 1. So I can move x squared to the other side, taking the square root for both sides, so I will have y equal negative or positive, a root of 1 minus x squared, which indicates the semicircle, the upper circle, semicircle, and the lower semicircle. So these are the two circles that we are talking about. Of course, this is not a function, because in the neighborhood of negative 1 and 0, for example, or if I'm talking about the whole shape, at any point here, I have a positive value and the negative value. So it's not a function. But if at certain points, if I restricted this semicircles into just only one semicircle, I will be able to deal with it as a function. So in general, this is not a function. If you discuss the case at negative 1 and 0 in specific, in the neighborhood of this point, at any point here within x, going up and going down, or making a horizontal, a vertical line, will cut the shape in more than one point. And this is why it's not a function. For this part, in the neighborhood of x minus 1, this is what I'm telling you about. But for these parts, these two guys, okay, here we go, these two guys, as you can see, at certain value of x, in this position, you will have just only one value of y. And this is because the function that you are dealing with here is y equal to the negative of the square root of 1 minus x squared. So for this guy and that guy, you will have just only two values within the negative size, within the negative bar. It's going to be a function. Okay, now you can see the substitutions, and of course at root 1 over root 2, you will get the value of negative 1 over root 2 as it is indicated. Which means sometimes for certain functions, under certain conditions, we can get the function which is a part of this, which is functions, but in the neighborhood of other points we can't, because simply you will have more than 1 point. This is what expressed in this shape, and it is represented that at the negative part, negative root of 1 minus x squared, the domain will be from negative 1 to positive 1, and the range will be from negative 1 and up to 0. Even if I want to get the h dash, it's gonna equal to 2 over x divided by the 2 of root 1 minus x squared. Simply, this is very, very simple, because this is 1 minus x squared to the power of half. Just differentiating, the power will go down, taking negative 1 from the power, so it's going to be negative half times the derivative of negative x squared, which is going to be a negative 2x times negative is going to be positive, so it's very, very simple. Also, all I said is why these 2 points in a specific, the function, or it's not going to be a function, this is going to be a relation. Because at 1 and 0 and the negative 1 and 0, these are like asymptotes or 2 tangents at this point. And the neighborhood of the points at x negative 1 and positive 1, these are vertical tangents as I told you. So you will find the positive and negative values in specific. If I try to get the gradient at these 2 points, which is going to be partial f partial x, partial f partial y, I'm sorry for here. This is also partial f partial x, partial f partial y. And of course, the equation is x squared plus y squared plus 1. So this guy is going to be a 2x and a 2 over y. And same way like for this guy too. So making the substitution at 1 and 0 and the negative 1 and 0 will give you 2 and 0 and the negative 2 and 0. And of course, these two guys have the value at 0, or the value of f derivative is equal to 0. This is why we can't get an implicit definition of y with respect to x, and which matches exactly our theory. So in order to be able to get an implicit definition of this function, the partial derivative for f with respect to y shouldn't equal to 0. And this is stated here. For any function where the partial derivative with respect to y doesn't equal to 0, we will be able to get an implicit definition. Also, if I make this equation, x squared plus y squared equal 1, in one side to be a function in x and y, it's gonna be of this form. Same results, same everything. If you make a partial derivative, you will find the partial derivative at these points equal to 0, negative 1 and 0, and 1 and 0. This is why at the neighborhood of these 2 points you can't find the definition of the implicit function. Other than that, it applies perfectly. So even we treat, as I told you, as a whole function, same results will be defined. This is for g of x squared plus y squared minus e to the power of xy squared. So this is a C-note function, said that can be written on the form. I can write it like this, x squared y squared minus e. This is g function from R2, and it can be written equal to 0. So getting at 0 and 1 and making the substitution is going to equal to 0, as I told you. So for c, or for the function at 0 and 1, it's equal to 0. The question is, in the neighborhood of the point 0 and 1, we can see the graph of g of x and h of x equal to 0, and from R2 into R2, h of x, y is going to be a continuous function, and these results assure that we have an inverse in the neighborhood of the point 0 and 0. So if you make this function, x squared y squared minus ex y squared, and you start to getting the Jacobian and make the substitution at 0 and 1, you will have 1, 0, and then partial g, partial x, partial g, partial y. Okay? And which ensures that partial g, partial y at 0 and 1, it's going to be as a direct relation from the Jacobian, as you can see, it's going to be equal to 2, which doesn't equal to 0, which means we can define it explicitly. I will continue this part, inshallah, next time, and I will review this problem once more. It's sufficient now for this introduction about the implicit function definition. Thank you very much, and till this is what's gonna be in the first midterm. I want you to start reviewing your course, and I will try to make a revision by the end of this week, inshallah. Thank you very much. It had been a pleasure being with you. Thank you.